Hello everyone, welcome to Technologies Discussion Channel. Today, I'd like to continue the discussion on amplifier. Okay, so for this video, I'm going to have various case study to study whether the amplifier is stable or unstable. So basically, in short, there are actually two possible scenarios. The first scenario is the amplifier is unconditioned stability, which means that the amplifier will be always stable. Another scenario will be potentially instability, which means that there is always a potential that the amplifier will be unstable. And hence, we need to have a few criteria so as to ensure the amplifier need to be stable. So basically, in short, we need to understand what are the criteria so as the amplifier will remain stable. So basically, this will be the objective of this video. This will be the part 13 series discussion on amplifier. So guys, if you're keen to know more about amplifier, please take a look on the playlist under the description. Over there, you will be able to find a series of discussion on amplifier. This is my email. If you have any so-called question, please send it to me. If not, if you want to have a faster response, please, you can always ask me through the comment. Before I continue, I'd like to urge you guys to help this channel by like this video. So this just take a few seconds, and it's free of charge. So guys, help this channel by press the like button now. For those who are new to this channel, please consider to subscribe and turn on your notification bell. Once again, thank you so much for strong support. Let's quickly determine why we need to have this stability analyzed, especially in RF, which means that high frequency. When we actually design an active RF circuit, it is crucial that we actually start off with a thorough stability analysis. So for example, when we design a amplifier, let's say, we need to ensure that the amplifier will work in a stable region. So therefore, every RF, we always study whether they will be oscillate or not based on certain criteria so as to ensure they work in a stable region. So we will explore the fundamental concept that is related to stability analysis, such as input and output stability circle, and understand how the arrangement of this circle on a Smith chart can indicate whether a device is unconditionally stable or potentially unstable. Accurate stability factor analysis is actually very important so as to prevent oscillation. So oscillation is undesired. When it actually oscillate, so basically it's beyond our control. So hence, we need to so-called ensure the amplifier won't oscillate so as to ensure they will be in a stable region. And therefore, with this stability analyzed, we will be able to achieve optimum performance in RF, more on RF, and also all those related systems. At high frequency, we always have a lot of unavoidable issue. For example, we have this unavoidable parasitic effect. So this can be easily cause the circuit to oscillate. For instance, let's say we have a poor ground skin. So this can result in coupling between different stages of multi-stage amplifier, leading to instability. For these sentences, let's say because of poor ground, and because of poor ground, we actually have coupling. Coupling means energy so-called jump over to different stages of amplifier. When this thing happen, so basically this is not part of our design rule. This can lead to oscillation, and therefore this also can be led to instability the design of the amplifier. Addition, some circuit in the RF circuit change may lack a well-defined source or load impedance. So which means that the load and the source and the load impedance are not well-defined, are not so-called fixed. For example, over here, the LNA, low noise amplifier in a receiver, they must interface with the external environment through the antenna. The antenna impedance can change. Let's say our hand actually touch the antenna, so therefore the impedance can change. This become an issue. So the LNA therefore must remain stable for all possible source impedance value across all frequency. So basically this is a key challenge in order to remain so-called stable, okay, we need to ensure the impedance, okay, that we actually design, all the impedance also must be stable, so as to ensure the amplifier will be remain in a stable zone. Instability can sometimes manifest in unusual way, such as abrupt change in the amplifier DC parameters. Okay, so the DC power supply, for example, they can change or increase sensitivity of the circuit to the surrounding. Okay, this means conducting a thorough stability analyze a complex and challenging task. Okay, so in the diagram above here, okay, the matching network are used on both sides of the transistor to transform input impedance and output impedance to the desired value of ZS and ZL. So this is the input matching network. So this is the output matching network. So in short, okay, so basically what I mean here, so basically is to transform the input impedance, for example, Z1 and output impedance to the desired value of ZS and ZL. Hence, in order to examine the circuit stability, okay, we need to model the active device as a two-port network. So basically, this is the so-called the circuit model here, as he mentioned here. Okay, so this two-port will be categorized through its S parameters and connect to impedance presented by the input and output matching network, ZS and ZL. So basically, this is, we just imagine you just remove away the so-called the impedance matching here, so as to get this is the so-called with the impedance matching network. This is without. Okay, so we can actually easily derive expression for the reflection coefficient. Okay, so this is the reflection coefficient for the input and reflection coefficient for the output. As you can see from here, this is reflection coefficient for the input. This is the reflection coefficient for the output. So how you actually can get, so as long as you have the so-called S parameter for the transistor, you can easily obtain this reflection coefficient for the input and also reflection coefficient at the output, okay, with this formula. So as long as you have the S parameters of the transistor, the above equations allow us to examine the stability of a two-port network. Remember, the magnitude of the reflection coefficient, they need to be in between 0 and 1. And most of the time it's 0 and 1 because it's a passive circuit. Okay, the reflected signal is therefore smaller than the incident signal. Okay, energy we can't create, so therefore reflected signal must be smaller than the incident signal. Okay, under the worst case, we have 100% reflect, then it will become a 1. If not, technically, it should be smaller than the incident signal. However, for an active device, okay, for example, if it's a amplifier, okay, with DC power supply, etc., so this will become an active device. Therefore, the reflected signal can actually experience a gain, which means that the reflected signal somehow can be bigger than the incident signal because the energy obtained from the DC source of the amplifier, for example, okay, rather than attenuation. In another word, for certain value of the S parameters, the magnitude of the input and output reflection coefficient of an active circuit can exceed 1. Okay, so basically, they can be more than 1 because if let's say we are going to have an active amplifier, okay, this can occur even when the source and load termination of the transistor are passive, okay, which means the source and the load, they are all passive. Additionally, okay, note that the reflection coefficient greater than unity, which is 1, correspond to an impedance with a negative real part. Oscillation is possible when either the input or output port actually exhibit negative resistance. Okay, so in the ideal world, there is actually no negative resistance, but this is just to symbol, okay, to means that oscillation actually occur. Okay, so there are two conditions as I mentioned on the first slide. So first condition is unconditionally stable. Another one is there is a potential that the amplifier will be so-called unstable. Okay, a two-port network is considered unconditionally stable if we can connect to any source and load impedance, okay, without result in oscillation. So in short, without any oscillation, okay, we can assume that the amplifier is always stable. So this is what this sentence means. In this context, we typically refer to any passive source and load impedance, okay, which means that the source and the load, they must be less than 1, as you can see from here. Therefore, for an unconditioned stable transistor, okay, the center point of the input and output reflection coefficient lies entirely within the unit circle of the Smith chart. Okay, so basically, this is what it means. Okay, so later on, I am going to have some example, okay, to study through when the amplifier will be unconditionally stable. Okay, a transistor that is not unconditionally stable is often described as potentially unstable. Such a device may become unstable for certain value of passive source and load impedance. Hence, it is very important to note that stability is frequency dependent. A transistor might be unconditionally stable in one frequency range. However, it can be potentially unstable in another. For this reason, okay, stability should be evaluated at all frequency point when you expected the transistor to be worked at. So basically, in short, you can see that this stability circle also vary, depends on frequency too. So therefore, it doesn't mean that if I design this amplifier at this particular frequency, okay, it is always unconditionally stable. Hence, I expected another set of frequency, it will be also unconditionally stable. So it's a no-go for this. So therefore, you need to ensure that all the frequency that you actually need to operate at that particular transistor or the amplifier, okay, you need to ensure that all of them are all stable. Okay, in mathematical language here, unconditionally stable actually require this rule here. Okay, so basically, you need to ensure that the amplifier will be unconditionally stable. You need to ensure that the reflection coefficient for the input and also for the output, they must be less than 1. Okay, when the above conditions are satisfied, the real part of the impedance of the transistor inputs and output ports are positive for all passive source and load termination. Okay, if these conditions are not met at a certain frequency, the transistor is potentially unstable at the particular frequency. If we set this, okay, the reflection coefficient at the input and output equals to 1. Okay, so earlier on I have mentioned that how to draw the stability circle. So when we actually indicate that it equals to 1, they are actually the arc of the circle. Okay, so you can always take a look on my previous video. Okay, so basically, they are actually under this scenario, reflection coefficient for input and output is equals to 1. Okay, they actually specify all load reflection coefficient that meet the magnitude of the input reflection coefficient equals to 1. Okay, because this equation specified the boundary for usable reflection coefficient L value. Okay, so hence it's supposed to be plotted in the reflection coefficient at the load plane. Okay, by the same, okay, for this reflection coefficient at the output, okay, they actually specify the usable value of so-called source of the reflection coefficient. Hence, it should be plotted in the so-called source plane here. So over here, you can see that this is the output reflection coefficient, and you can see that this value is actually depend on the source reflection coefficient, and hence because it depends on the source, hence this part must be plotted in the reflection coefficient at the source plane. So this is what you want to say. Okay, so before I come into the discussion on the various case study on the stability circle of an amplifier, okay, again, if you have learned something from this video, please help to like and subscribe. Okay, so let me continue on the different cases of stability circle. Okay, so when the stability circle intercept the Smith chart, okay, you can see that they actually cut a portion of the Smith chart. Okay, the device is potentially unstable. Okay, so once they cut, there is two zones. Okay, one zone will be stable, one zone will be unstable. Okay, so later on I will discuss how can we determine. So basically, in short, if any stability circle they cut into the Smith chart, there will be two zones. Okay, one zone will be stable, one zone will be unstable, and hence we declare that the device is actually potentially unstable because we need to have a condition in order for it to be stable. If the magnitude of S11 and S22 was less than infinity, so the center of the Smith chart produce a stable region of operation. When it's opposite, when it's actually more than 1, okay, the S11 and S22 more than 1, then the center of the Smith chart was in the unstable region of operation. Okay, so what does this mean? For example, under this scenario, when you look at the equation here, when the magnitude of S11 is less than 1, okay, which means that the center point of the Smith chart, okay, so this is the center point of the Smith chart, which means that this part will be stable. So this part will be stable, which means that this part here will be unstable. So this is what I mean. On another scenario, okay, when S11, okay, is actually the magnitude of S11 is greater than 1, which means that the center point of the Smith chart is actually unstable. So this part will be unstable. So hence over here, I can declare that this part will be so-called stable. So basically, this is the key difference. Firstly, before you actually work on the stability circle, okay, you need to look at the magnitude. Okay, for example, if you are going to look at S11 or S22, it doesn't matter, it's still the same. For this case, I just illustrate as S11. Okay, so basically, if it's less than 1, the center point will be stable. Okay, so after that, then we declare that this part here is unstable. However, if let's say S11 is more than 1, the center point is unstable, so therefore the other part will be stable. So basically, if you want to ensure the amplifier to be stable, okay, so therefore you need to ensure that they actually work in this zone here. For this case here, if you want to ensure that the amplifier is stable, then you have a bigger so-called portion of space to work, okay, for the amplifier here. Okay, so basically this is the first criteria. Okay, look at the magnitude of S11. Next, okay, so it is also possible for the intercept stability circle to enclose the center of the Smith chart. Okay, so again, this will provide two types of arrangement. So earlier on, it's just cut a small portion of the Smith chart. So now this thing actually cut into the center of the Smith chart here. So again, it's the same rule. So when they actually less than 1, which means that the center point of the Smith chart is stable. So therefore, this part here will be stable. The rest will be unstable. Okay, because it's less than 1, so therefore the center point is always stable. So therefore this part here will be stable. The rest will be unstable. Same, let's say if it's a reverse. So now the magnitude of S11 is greater than 1, then the center point of the Smith chart will be unstable. So this part will be unstable, which means that the rest of the part will be stable. So basically, this is another way. So this first way is basically the circle just cut a very small portion. Okay, so this part cut the center. Again, just look at the center of the Smith chart. Whether is it more than 1 or less than 1. If it's less than 1, the center will be stable. If it's more than 1, the center point will be unstable. Then you will be able to craft out the another region. Next, okay, the stability circle might also be entirely inside the Smith chart. Okay, so basically this circle here, the output stability circle, they may be inside the Smith chart. Okay, so the rules is still the same. Okay, by looking at the magnitude of S11, okay, whether they are less than 1 means that the center point here is actually stable. So this whole part will be stable. So for this condition, we will say that it is always stable. Okay, because they are part inside this Smith chart here. So this is what we call the unconditionally stable. Okay, for this part here, okay, so basically you can see that the center point will be unstable. So basically they will be always unstable for this form of design here. Let's say if you look at the output stability circle here. Next, okay, the figure illustrates a case where the input stability circle intersects the Smith chart but does not enclose the center of the chart here. So basically, in short, this is another one. Earlier on is just on S11. So now I actually change to S22. So instead of output, so if you see earlier on, they are all output. Okay, all these are all output. Okay, but over this case here, if let's say it's a S22, this will be an input stability circle. That's all. Okay, how you determine is the same. Okay, so less than 1. Okay, so basically this is so-called less than 1 here. Then this part will be stable. So if let's say it's more than 1, this part will be unstable. Then therefore I only have this stable region here. So the rules of S11 or S22 is still the same. Okay, by looking at the magnitude, okay, then you will decide whether the center point is stable or unstable. Then after that, you can actually easily carve up the stable region or unstable region. Okay, so basically this part, like I mentioned here, is to illustrate S22. So therefore you can see that it become an input stability circle. Next, okay, some value of the termination produce an unstable operation. To have unconditional stability, the stability circle should either fall completely outside of the Smith chart or completely enclose the Smith chart. Okay, so earlier on I already showed those completely inside the Smith chart. Okay, so the figure below actually have this scenario. Okay, so basically you can see that this is completely outside. Okay, completely outside. So basically this part will be stable. So basically they will be all stable here. Okay, so this is the stability circle. They circle the Smith chart also. Again, this part will be stable. So therefore, this will be a stable region here. Okay, so if either S11 greater than 1 or S22 greater than 1, okay, the network cannot be unconditionally stable, okay, because you already have this kind of so-called use case here when they are actually greater than 1, okay, there is no way that they can be unconditionally stable. In those cases here, either the termination, okay, actually they can easily lead to unstable operation. Okay, so with this, okay, I'd like to end my discussion. Okay, please up to like and subscribe. Once again, thank you so much for your strong support. I hope to see you guys soon. Bye for now. Thank you.